And with that, let's get started. So the first question is, what is Tezos? Right? Sort of a very brief, high-level overview of what Tezos is. And I should have my notes with me here. So Tezos really is a decentralized, permissionless, and censorship-resistant public blockchain. And this is quite important because it allows you to deploy any sort of application that can fit and run within the virtual machine that Tezos has, and no one can censor this or can stop you from deploying it. This is very different than sort of the existing computational model where you have to deploy to AWS or Google Cloud or run on your own physical hardware, but it's relatively simple to censor and stop those applications. So there's this, and the other thing, it's trustless in the sense that users can very easily check what code is actually being executed, and if that's the code that's being if the code that's on chain is going to be the one that's executed. So there's very little room for the operators to cheat. Right, it has smart contracts, and we'll talk more about them in a little bit. And it is one of the first live, I think actually the first live proof of stake network that is actually secure in terms of proof of stake. So Tezos launched in June 2018 with the BetaNet, and maybe I should write some of these things down. Proof of stake. So it's proof of stake, which is a lot less wasteful than proof of work in terms of energy consumption, and also has a bunch of other interesting features where it's in proof of work, the security of your network is extrinsic to your chain, whereas in proof of stake, it's intrinsic to the chain, which means that we can build protocols that actually understand how the chain itself is secured and can sort of modify the security parameters. Due to that, it is very likely that proof of stake is probably more secure than proof of work in the long run, because we have, as a community, as the token holders of these networks, much more control over the underlying security of these chains. The second really important point about Tezos is it has governance. And again, here it's the first chain that actually launched with governance inbuilt. And when I say this, I mean Tezos is a governance process that is defined on chain. So almost all chains that launch, I just want to switch speakers. It's kind of strange for me. Yes, there we go. Now I can also see. So Tezos has governance. And it was one of the first ones to have a governance process that's described and encoded on chain. Things like Ethereum and Bitcoin have governance, even though they sort of don't publicly say that they have a governance process. But of course, any existing system has a governance process by which people make choices on the underlying system. In Ethereum's case, it's mostly an oligopoly, where a bunch of people will come together in back rooms to make deals on how the system should evolve, which leads to, first of all, that process being very opaque and at the same time very slow, which you can sort of see. We'll talk about this in a bit as well, but Tezos has undergone pretty much a network upgrade every 4 months that added more and more useful features to it, whereas Ethereum had 3 hard forks in its lifetime and really hasn't changed all that much from inception. Yes, so this is sort of governance. What is Tezos? Any questions on the high-level idea of what Tezos is? So it's a smart contracting platform that is decentralized, permissionless, and censorship resistant, and has a governance mechanism inbuilt. Any questions so far? Otherwise, we can move on to the next topic. Okay, I think this is okay then. So I just briefly want to talk about what else exists in the industry, right? It is very easy to become sort of very pigeonholed into a specific thing. But especially within the open source community, it's always very beneficial to learn from what others are doing to try and figure out whether you can work with others. So due to that, I'd like to spend a couple of minutes just thinking about and talking about what else exists in the industry today. So we have chains such as Bitcoin, right? Bitcoin doesn't really offer smart contracts. Its entire idea is that it's proof of work. It's a sort of most secure proof of work chain, and maybe it has the claim to become money in the future. We'll see. Then we have Ethereum, and Ethereum is somewhat similar to Tezos. Right? Ethereum also has smart contracts. It's proof of work, though. It doesn't have a governance mechanism. There is no huge sort of upgrade mechanism in place when you compare this to Tezos. Then you also have things like Cosmos and Polkadot. Which are really interoperability solutions. And whether these will be valuable or useful is yet to be determined, because we really have not yet explored the concept of interoperability within blockchains. So Cosmos really is focused on building a routing hub for messages between blockchains, and Polkadot is roughly trying to do the same, but also provide security to other systems. So these systems aren't smart contracts in that sense. And then now you start to have sort of a third wave of things which aren't live yet. So Polkadot is also not live, sorry about that. But you have things like Near and Solana and Celo, which are sort of a combination. Oh, by the way, also all of these are proof of stake. So are these. And these are sort of proof of work. But these don't have smart contracts. And Near, Solana, Celo will have smart contracts that are also proof of stake, but it's unclear how these systems will fit into the industry. All right, let's quickly erase this. Okay, so now as the third thing I'd like to talk about is really sort of a high-level comparison of Tezos and Ethereum. Right. So how do they differ? How are they similar? So we have Tezos on one hand here, and then we have Ethereum. So both of them have virtual machines, meaning that you can have smart contracts that execute on these systems. In Tezos, this is a Michelson virtual machine, and the programming language is called Michelson, and we execute Michelson contracts on chain. In Ethereum, we have the EVM. Michelson sort of took a lot of learnings from what didn't work in the EVM. Michelson is strongly typed, so it's fairly easy to do formal verification of the smart contracts that are actually being deployed to the system. So you can get very low-level guarantees that the smart contracts do what they say they do. Whereas in the Ethereum virtual machine, this is really not possible due to the fact that this is effectively sort of an incredibly low-level virtual machine over which to do formal verification is very difficult. However, as developers, most people aren't going to write their contracts in either the Ethereum bytecode or in Michelson. So we have a bunch of higher level languages. In Ethereum, this is really only Solidity. There was this try to get a language called Viper, which looked closely, was like sort of like Python, adopted. That never happened. And it sort of just fizzled out. It's still around, but no one really uses it. So in Ethereum, you only have Solidity. And believe me when I tell you that writing Solidity programs is not fun. And it's incredibly error prone, which is what we've seen so far, right? In Ethereum, even the people that built the underlying implementations for the Ethereum virtual machine, in the case of Parity Ethereum, wrote and deployed smart contracts to Ethereum that were so broken that they lost, I think at the time, $100 million. This is the last Parity Ethereum hack where they lost access to the sales from the dot sale. In Tezos, so it's much earlier. So we have none of these languages are sort of as battle tested as Solidity. This is one of the downsides, but we have a couple of languages actually. So we have LIGO, we have SmartPy, We also have something called Lawrence. Eventually, we'll also have something called Juvix, which I spoke about earlier, dependent types for smart contracts. So maybe this is still very early on. This is still research, so it will take a couple of months before this gets ready and is usable by the public. But LIGO is kind of nice because it has a couple of different front ends. It has Pascal LIGO and Camel LIGO right now, I think. So whatever, if you're a Pascal developer, you can easily pick this up. SmartPy is metaprogramming in Python, and Lawrence is metaprogramming in effectively Haskell. All of them compile down to Michelson, and so the contracts that you deploy are Michelson, but you don't have to write Michelson by hand, which is a huge benefit, by the way. Writing Michelson by hand is annoying because it's a stack-based language. So it's much nicer to sort of write a contract in something like LIGO. Then you get as an output Michelson. You can look at the Michelson code yourself, formally verify if you want to, and then deploy the Michelson code to the chain. And now maybe some of these vanity metrics that people like to talk about. How many transactions a second do you have? Well, in Tezos, we roughly have 30 transactions a second. In Ethereum, we roughly have 15. The thing is, in Ethereum, this number isn't going to change, at least with Ethereum 1. This may change in a magical future world where Ethereum 2 actually works. In Tezos, it is very likely that in the next year or so, we will bump this by an order of magnitude, at the very least. This all comes down to the fact that Tezos has an active governance process and has multiple core development teams, out of which I built one of them, and the other one is Nomadic, and the third one is Lambda in Japan, that are actively working on shipping useful upgrades, so every 3 to 6 months, that improve the underlying system. Right, and we talked about this a little bit. So we have security, Tezos proof of stake, Ethereum proof of work. For consensus, it's ME plus in Tezos, which is effectively Nakamoto consensus. And in Ethereum, it's also just Nakamoto consensus. Nakamoto. Again, this will change in a relatively soon in a protocol upgrade to add finality to Tezos. So that is yet to come, but it's in the works, finality, where hopefully we can get instant finality by using something like a finality gadget in order to finalize blocks. And then the last thing we have here is governance. And in Ethereum, we have an oligopoly. And in Tezos, we have coin voting. And just to explain you a little bit what coin voting actually means, it means that in Tezos, anyone can inject a proposal, so a new software upgrade that the network should upgrade to, and then the entire community of XTZ holders, and by community, I really, in this case, mean XTZ holders, can vote on this upgrade. And if a supermajority of them accept it, then the upgrade will automatically get deployed to the chain. Right. Any questions on any of these topics so far? Does any of this make sense, or am I speaking total gibberish to you that no one understands what I'm saying? There we go. Okay. I think this is probably a good sign. In this case, I quickly want to go through the architecture of Tezos. So how does Tezos actually work? Architecture of Tezos. Because it's important to understand how.
Just a second. It would be great that you capture the whiteboard in order to make it more visible, because the whiteboard, the way you write is not so readable. But if we have a better screenshot of the whiteboard, it would be great. Yeah.
Okay. Yes. That's actually a good point. I'll take.
Sure. I don't know. I mean.
Thank you, Adrian.
Okay. This is. I'll also try to write more cleanly. Yes. So architecture of Tezos. So how does Tezos actually work in practice? So most blockchains really have a sort of a threefold stack. You have at the very top, you have the protocol. Then underneath that, you have a consensus mechanism. So how do nodes agree? What is the canonical chain? How do you extend that chain? And underneath of that, you have some P2P layer that exchanges messages. And these lower two parts, this distinction isn't necessarily super clean. There's some bleed between the protocol and the consensus. But generally speaking, this is part of the shell. So this is the sort of the environment that the protocol runs in. And the shell cannot be upgraded through voting on chain. However, the protocol, in the case of Tezos, is written in OCaml. And the way this works is kind of fascinating because you have effectively what you can imagine as as an abstraction layer between the shell and the protocol. So the protocol can be upgraded via on-chain upgrades, meaning that anyone in the world can write a new protocol version in OCaml, inject it to the chain, and if people agree with it, then the shell, the node, will automatically download the new protocol, compile it in a restricted subset of the OCaml compiler, and hot link it into the underlying shell, into the running shell. Due to this, there's almost no way to prevent from a protocol upgrade going through, right? Imagine what would happen if someone injects a protocol upgrade which removes all economic incentives or which punishes a single validator because a single validator is behaving maliciously most of the time. And so we can't slash this automatically in the protocol, but rather we have to manually slash this. In things like Cosmos, the validator set as a whole could just refuse to upgrade. They could just stop their nodes and say, we aren't going to support this hard fork. We want to stay on the existing protocol. We ignore what governance said. In Tezos, we have binding on-chain upgrades. That means if something gets voted on in governance on-chain, every node on the network will upgrade to it. Sure, you can block this specific protocol hash, right? You can block this specific protocol hash, but then someone else tomorrow can go add one comment, changes the hash, and re-inject the protocol. And then people vote again, and eventually the system will upgrade to whatever the majority of coin holders wants. This is quite important because it makes the system very resilient against external capture of actors that don't necessarily have much stake in the system. Yes. And really the way you can the way I conceptualize this abstraction level is that you can think of the protocol as something that is running in its own process and only talking over RPCs with the node. And there's sort of a very clearly defined interface between the protocol and the node. And as long as another protocol adheres to the same interface, it is compatible with this node. There's also a second type of upgrade in Tezos. What happens, because let's assume, so the shell exposes an interface to the protocol that can be used by the protocol. But for example, maybe we want to add new cryptography. Maybe we want to add BLS signatures, and we don't want to have to implement all of the cryptography within the protocol. Maybe we just want to bind to some Rust libraries and expose them through this interface. In that case, that's called an environment upgrade. And what happens here is that everyone will have to update the shell or the node in order to update the interface that this node exposes. And then the protocol can have access to all funky new functionality, such as null cryptography. This is most likely going to happen in the next upgrade, so in 007. We will try and upgrade the environment at the same time because we want to add a bunch of new cryptography to the protocol in order to support zero-knowledge proofs much better. So specifically, we're planning to add BLS signatures or BLS cryptography, exposing both the Michelson as well in the interface. Yes. And so this protocol is really, it's the rules of the game. It's the economic rules of the game. So it says, how do you create an account? How does governance work? How does slashing work? How does staking work? This blob is where I spend sort of 90% of my time in order to make it better in the future. Right. Let's also very quickly talk about the proof of stake mechanism. Let me start off by saying that proof of stake is not consensus. They're two separate things. Damn it, if I had slides, I could flip back to the previous slide. But proof of stake is not consensus. Proof of stake is a civil protection mechanism. It determines who is allowed to participate in the underlying consensus. Because consensus can either be something like Nakamoto consensus, so longest chain, heaviest chain, what Bitcoin is using. And then proof of work is how you select who is allowed to participate in the Nakamoto consensus instance running on the network. In Tezos, we have, for consensus, we have ME+. And this is effectively a variant of Nakamoto consensus, heaviest chain. And then we have a novel proof of stake mechanism called LPOS, liquid proof of stake, that determines who's allowed to participate in ME+. And there you have staking. So anyone with at least one role can register to become a validator on the network, or baker, as you call them in Tezos. And you need at least 8,000 XZ for this. And then you assign one role. So we measure everything in these arbitrary units of 8,000 XZ called roles, just to reduce the computational load on the nodes themselves. And so people participate in this, but let's say I only have 8,000 XZ. I sort of start my operations, but then people can delegate to me. So there's this notion that if you have, let's say, 10 XTZ, you can delegate them to someone. Delegate here. Delegate to some validator. And this validator, right, there's also, in order to incentivize people participating in the security of the network, there's also sort of inflationary rewards in Tezos. So every year there's decreasing over time, since this is a fixed number. There's a 5.51% new issuance of rewards. This means, yeah, so a year, but this is going down over time because these are fixed numbers per block instead of actual percentages. 5.51 was just what happened effectively on the first block of the network. And this gets distributed to validators. And these validators, it's up to them how they want to share this reward with the people that delegate to them. Most people share 90% of those rewards back to the people that delegate to them. But most importantly, why is this actually secure? Because in proof of work, you have to make a choice which fork you mine on, right? I have to decide, do I put my ASICs to work on block A or block B? And this is a mutually exclusive choice. In proof of stake, we're only signing with cryptographic keys. I can create 10,000 signatures a second. So I could sign on all possible blocks here. But if you do this, then the network never converges to canonical history, and we sort of end up in this massive, ever-growing tree where we don't have a blockchain anymore, but rather we have a tree that is completely useless. So how do we solve this in Tezos? Well, in Tezos, we say a validator has to put up a security deposit for each block that they create. And let's say you put a security deposit for A, and this is at height 5. And now we've put some X amount of security deposit. If you sign a different block at height 5, again, let's say you change some of the transactions that are in the blocks, so the block hash changes at height 5 as well, then we slash your entire security deposit. So all of a sudden, there's now an economic incentive to not build on every possible block you see, but rather to choose the correct block according to the consensus. This is really important. Things like EOS and BitShares and Steemit don't have this. And due to that, like these systems are completely insecure in terms of how the underlying consensus and the civil protection mechanism works. All right, okay, now let me quickly take a picture. that I can share with you guys later. Okay, picture done. Right. Right. Quickly, let's talk about governance and what has happened here historically in Tezos. So anyone can inject a proposal. Then we have 8 cycles for bakers to upload this proposal. In the future, we will also allow individual token holders to override their baker's vote, as long as you have more than one role as an individual holder that is delegated to a specific baker. This is actually something we're working on for the next upgrade. Then you have the next phase, which is the exploration phase. This again lasts 8 cycles. In here, so here you can have many proposals, and only one will continue to the next phase. Then during the exploration phase, you have to reach a minimum quorum, which is adaptive based on past participation. And then if quorum is reached and 80% supermajority wants to explore the current proposal, then we go into a testing phase. The testing phase is kind of funky because what actually happens, the product testing phase, the node will automatically spawn a test chain that anyone can use with the proposed protocol. So here we test things like, does it actually work in practice? Can people send transactions? And then any user can start testing on this testing, on the test chain that runs during the testing phase. And then lastly, what is it called? Proposal, exploration, testing. I'll call it approval phase. I think there's another name in the official docs for it. But the approval phase is effectively just saying, we've now tested this protocol upgrade. Do we want to upgrade mainnet to it? And if, again, here we reach quorum, which is adaptive based on past participation and 80% supermajority, then mainnet will upgrade to this injected protocol. And again, all nodes will automatically upgrade because they will download the latest, the source code from the network, compile it in a restricted subset of the OCaml compiler, and then dynamically link it into the running node. Quickly for the history of upgrades. So currently we are on, as of today, on protocol 006 or Carthage. Carthage was a housekeeping proposal that fixed sort of a bunch of things that weren't super nice, so small bug fixes. Before this, we had 005, which was Babylon. And Babylon was a massive protocol change where we effectively migrated the entire account state, because in the past, what you were only able to delegate from K2-1s, so from smart contracts, but they weren't actually smart contracts. There was just this weird structure where they didn't have any code and they were just used for delegation. And in Babylon, we migrated all of this. We also introduced ME+, and we also made Tezos delegatable. Before this, we had 004, which was Athens, which just tested out whether the upgrade mechanism works, and it just changed the role size from 10,000 to 8,000. I still find it kind of annoying because before you could very easily see how many roles you have and go to how many tokens you have and vice versa, because it was it was in the order of tens. Now it's 8,000 per role, so the math becomes harder to do in your head. And before this, we had 003, 002, and 001, which were the original protocols. These were still effectively hard forks by which you upgrade. So we didn't have a governance process here. So Athens really activated the governance process, but these happened sort of in the first 3 months of the network. Yes. Also take a picture of this. Done. Okay, now the last part. So this is sort of a lot of background for how Tezos works. How the governance mechanism works, how the consensus works, how, yeah. And now we will talk a little bit about the actual thing, Tezos versus Ethereum. So one of the main reasons why, in my opinion, Tezos is a very decent choice for smart contract developers right now is because it's very unclear at this point in the industry on whether, on what the specific use cases are going to be that this industry actually solves for the real world. So really, this is super early. This is the internet in 1992. No one really knows what's going to be the next big thing. But with Tezos, you're betting on the fact that you have governance. So in Ethereum, we have a fairly static system that hasn't changed much since inception, but is currently trying to go from Ethereum 1 to Ethereum 2, which I like to compare to going from the Stone Age to straight to space travel. It's very unclear to me whether this will actually work. In Tezos, due to the fact that you have a governance process and an active core development community, you're much more betting on the fact that over time, Tezos will continue to evolve. And sort of as new and novel research and applications appear in this industry, Tezos is one of the only chains, actually, I think currently the only chain that has the ability to effectively integrate these changes over time. Right? So in Ethereum, so you have to bet that what is currently possible in Ethereum is what will be needed in 10 years. You have to do the same bet with Bitcoin. Bitcoin isn't going to change. With Ethereum instead, with Tezos instead, you can bet on the fact that it will upgrade over time in an incremental fashion. So instead of introducing incredibly large features, so you go from Stone Age to space travel, we sort of, every 6 months, we ship new upgrades that are useful for the network and that sort of iterate and improve upon use cases that we've seen in the real world. Due to this, as smart contract developers, sort of if you run into a problem on Ethereum right now where something is not possible because 3 years ago no one had designed for it, you're kind of stuck. In Tezos, if you have a real use case that currently the protocol can't support, it is very easy for people to bring this up and and the protocol and for us to adapt the protocol to that use case adaptation. Right? Imagine that adaptation. Yeah, it seems correct. Imagine right now you realize we need specific cryptography. Maybe you want to interoperate with something like Coda. Maybe you need the MNT6 and 4 curves. No protocol has access to them, like Ethereum isn't supporting them. It's not feasible to write that cryptography in a Solidity smart contract. If this is a real use case that a majority of the network has, it is very easy for us to add this into the next protocol upgrade. And then in 6 months from now, all of a sudden you have access to this novel cryptography. I think this is by far the strongest point for Tezos right now, that we are not clear yet what specific problems smart contracts will solve. And due to that, it's very hard to design a static system to solve all those use cases. But in the Tezos case, you can bet on the fact that the underlying protocol evolves over time in order to take into account these use cases. Sort of some of the downsides that you have to be aware of deploying to Tezos over Ethereum is a lot of the tooling is a lot newer, so a lot less battle tested, right? So Solidity has been around for 30 years. It's fairly battle tested. To be fair, it's a shitty system. It's a shitty language, but it's a working language. LIGO, SmartPy, Lawrence, they're all much newer. Due to that, it's sort of, there may still be bugs. So just be aware the tool chains haven't been tested by thousands of people yet. You are some of the first beta testers. On the other hand, this also gives you great input in how these systems actually evolve, how these tools evolve over time. Yeah, and the other thing is the standards in Tezos, for example, token standards are currently being formed. So again, sort of it's work in progress. But the nice part about this is that as an application developer in Ethereum, you have very little say in how the underlying system behaves. Right now in Tezos, you as an application developer can have a lot of input in how the system evolves and what the needs of application developers actually are. So just keep this in mind. Right, that is sort of benefits of Tezos versus Ethereum. That is a shitty slide, and I'm sorry for this. And then as the last thing, right, are there any questions? So this is effectively sort of a quick introduction to Tezos and applications and languages on Tezos. Are there any questions in the audience?
Questions? Nope. I guess we have we have a few minutes left, Adrian. So it might be time to conclude.
Yeah. So in that case, thank you very much. I hope you enjoyed this talk. I hope this format works. To say virtual conferences are kind of interesting, and I like them because they require less travel and less waste there. Thank you very much for listening to me. I'm Adrian, one of the founders of Cryptium Labs, and thank you very much.
Thank you, Adrian. Okay, so next any questions now? No? Okay, thank you. The next speaker will be, the next speakers will be Christian Hinderknecht and Rémi Le Sénéchal, I guess. Please come here.